All right, so I'm talking about HPNA today. What is HPNA? It is the stupid acronym that I always toss around, which means a lot of nothing. It's a bunch of marketing mumbo-jumbo, but it's the only term that you can really use to refer to this stuff. HPNA is the Home Phone Line Network Alliance. Why is the Home Phone Line Network worth anything? Well, we'll talk about that. It's robust as heck, and if you don't use it on home phone lines, it's even more robust. HPNA is not taken seriously generally by people I've talked to. I've been working with Ameritech people to try to get dry copper from my house to ISPs near me on Williamson Street, and they're more or less assholes. They don't want us to provision dry copper services even if you're served by the same wire center, which means that the two locations in question both are served out of the same CO, so the pair that goes to them and a pair that goes to me both land in the same building. If I worked for Ameritech, it'd be easier to just be a temporary employee and cross-connect the pairs that I need between those two locations. If it works, great. If not, tough luck. But the trouble you've gone through so far hasn't gotten very far. So it got me thinking about how I might want to proceed. And it seemed logical to tell these engineers what I was doing. I was initially playing it off, saying, I need dry copper, I need this much bandwidth, yada, yada, yada. And they'd say, well, why? And I was like, well, I just expect that I'll be putting signaling on this line that needs that. That didn't get them going because they want to know what line format you're going to use. They want to know if you're going to use like DSX1 signaling, T1 style, if you need conditioning for higher frequency response, yada, yada, yada. They also don't expect you to know limitations on output power. Well, it's not that hard to find it. SEC publishes these things. So I know what limits I can work within. However, proving that to them is not possible. If I were a CLEC, it'd be a little easier. Doing some research, by the way, at the PSC in Madison, it takes $250 in one exam to become a CLEC. So you too can be a CLEC. When you do that, you have a couple of cool things you can do. After I researched this with PSC, services that had been sold in the past under agreements by the RBOC or whoever happens to control the physical access or whoever is the LEC in the area, if they had an agreement with another CLEC in the past, I as another CLEC could say, based on this agreement, I want that service at the price you quoted this customer, which is a bad thing for the telcos because it lets them be not cheated, but they can basically get less profit out of current things that are happening with other CLECs if CLECs who are purchasing new services can say, based on this contract you sold this service to this other CLEC with, I want to go ahead and do that same thing. Recently, there's a couple things that have changed. The PSC now can have tariffs change in 24 hours by a telco. It used to be months. So if you do as a CLEC, if you do become a CLEC, and go and say, I want this service, here's the agreement I want you to give me pricing based on, they can change it a day later. So it's almost a moot point that you can fall back on previous agreements. But suffice it to say, you can become a CLEC without a lot of effort. The exam basically is a cross-section of more or less technical aptitude, understanding of FCC limits and regulations, knowing how to provisioning, knowing what the code styles are for Ameritech. So you do have to do some initial work to figure out what all this stuff is. You can't just go and become a CLEC if you're an electronics student. There's a lot of additional knowledge that isn't well documented, but is available from Ameritech or anybody who is the local person, who is the LEC in the area. That's side data. So anyway, my goal though was to try to get together some data on the line stuff, the stuff that I'd be running over this dry copper. So when I go to these engineers, I have something more to say than I want this frequency response. So I started telling them what I was working with. And they would say, HPNA, I saw that crap at Best Buy. You can't use that. Just because it's at Best Buy, obviously, it can't go in copper. Or they would say, well, if you want 10 megabits of access between these 2 points, just get a fractional DS3. Excuse me, that's 10K a month per point. So not in reach of me, at least. So, but within that, they would also say 3T1s. That'll be close enough to 10 megabits. I'm like, sure, so that's 6 pairs of wire that I have to pay for, and I have to pay for engineering each month to maintain if the signal goes down. It's three installations at once. You can't get bulk discounts for this kind of stuff either. So the options are limited between that 1.5 megabit magic boundary and 45 megabit magic boundary. So right in that dead zone, what do you have? You have dry copper in a lot of locations, but how do you use it? SDSL stuff right now can push symmetrically 2 megabits, give or take a couple megabits depending on conditions. But suffice it to say, 10,000 feet is reachable at 2 megabits. Well, that's fast, but what if you want to do reasonable amount of shoutcasts? And what if your upstream is close enough to you, but you have no line of sight for wireless? You're still stuck. You're stuck with the telecom unless you can get them to budge on dry copper. So let's say you do get some dry copper. Well, those megabit modems made by Paragain, Paradigm, ADC Cantrox, a lot of these companies that have 2 megabit Ethernet bridges will want $500 to $600 per endpoint. That's out of the reach of my abilities right now, for sure, just for a project like this. So what else is there? Well, looking at what's driving broadband access right now, a company called Broadcom makes a common broadband controller CPU. Basically, it's a souped-up DSP meant to put highly dense data onto a copper loop and send it. The same Broadcom chip that runs HPNA bridges, the Netgear cells and NetWinksys cells, is the same one used in the RCA cable modems, the surfboard modems. Broadcom is the de facto reference implementation hardware for HPNA, for DOCSIS, for QAM modulators. That sort of thing is done on their hardware. Lots of CPU to do it. So looking at what they made, I started to see who was using their chips. I saw that Linksys and Netgear both bought it. This is before I knew what HPNA was about a year ago. So I started researching it, saw that 3Com also used it, so I went to 3Com's site, checked out their home networking area. And lo and behold, there's a picture of a PCI, a 3C410. Can't get support on it anymore, that number is no longer searchable. But the 410 is their home PCI HPNA 10 megabit interface. And I started reading about this and saw that they were getting, amazingly, 10 megabits of throughput over random crappy copper wiring in a home. What's the significance in that? Well, a lot. In a home network, you have a star. Basically, in most homes, you have line 1 present at multiple locations. It's either ran star configuration, maybe, to the DMARC, where every single jack in your house is home run to the one location at your DMARC or near to it. Or in older homes or lesser, or homes that had electricians who maybe didn't give much thought to it or didn't care, they will maybe do a home run to each floor of the house, and then parallel run sequentially from jack to jack to jack to jack in that floor. That same line will appear there. So you have a couple of situations where you have random star wiring, or star wiring to the home run, and one line that goes way off to the yonder there, 5 phones on that, and you have a lot of random characteristics of that. That wire is not like Ethernet. It's not high quality. It might not even be Category 1 wire. You may only be looking at 8 to 10 megahertz of response. Category 5 easily can get you 120 megahertz of response end to end. So home wiring is much, much worse than Ethernet wiring or categorized wiring. But with that in mind, that basically parallels in ground wire. So if you want to get data over a line and not spend $1,000 for the thing, what are you going to do? To me, HPNA seemed like a good solution. So I conned a friend into buying a pair of 3Com Home Connect cards, put them into machines at Herzing, spent the afternoon there, trying out a variety of media. Found out that it would work over wet paper towel, about 1.5 megabits at about a foot. Power bars connected end to end. 6 of them connected end to end were yielding about 8 megabits. A 100-foot spool of Romex, the AC wiring in your home, was again about 7 to 8 megabits. What other media would you try? We'll get to the cool ones that I tested later.
Spoon with salt water.
Yeah, spoon with salt water. Basically any electrolyte that would be about 100 to 200 ohms of DC resistance will be functionally good enough for HPNA to put its signaling through. Very robust protocol, but it is that because it was meant to work on homes that have virtually no guarantee of reasonable communication wiring being there. So essentially anything that's conductive and not too noisy will be fine for HPNA. So as a good forward, that's essentially what I was looking at. These pair of 3Com cards are doing amazing things, and I started looking at what was being implemented with HPNA in it more and more. Dell makes these little MP3 players that can plug into a network. They have Ethernet and, ta-da, HPNA on them. So interface it to a home network with no additional effort. So Dell makes one of these MP3 players in the network. So does Turtle Beach, called the Audiotron. It has the ability to play MP3s, waves, whatever. It scans a subnet for an SMB share on machines, looks for default names of My Music, media, that kind of stuff, traverses the entire folder tree, builds an internal index, and over HPNA you can play this stuff. It's beautiful. 10 megabits of throughput is more than enough for MP3s. And there's also products from Linksys that have integrated basically IP telephony into a single port bridge. For example, in your house, you can plug this device into your phone line, speaks HPNA to any other devices out there, and provides voice over IP gateway access to Tell.me or net to phone. You can pay a minimal amount of money, like 4-cent long distance, basically by using this voice over IP bridge. But it all coexists in the same wiring. It's pretty cool that way. These products also coexist with other services that fall on the same phone lines. And I have a graph of the spectral layout of where HPNA fits within all this mess. As far as where the spectrum it operates is, 4 to 10 megahertz is HPNA's range. Actually, 4.2 to 9.5 is the main spectrum of frequency that it operates on. Obviously, you see it coexists with DSL, ADSL, or SDSL, and pod service in the same line. This is very high-frequency signaling, so you don't even hear it on a phone. Interference is virtually non-existent. Most phones attenuate quite well above 100 kilohertz, so the chance of this stuff making it all the way to your ear, very remote. As far as how this stuff is arranged, this is just like Ethernet. So the same frame format you have on terrestrial Ethernet is essentially at work in Ethernet, is at work in HPNA. The 802.3 body had a good amount of documentation generated since the inception in the 70s, and HPNA, or the home PNA, the home phone line networking alliance, took that as a model and decided it was a good enough one to work with, obviously, because Ethernet kind of is everywhere at this point. There's not a single device you can really not put Ethernet onto. Maybe cost will stop you. But in any case, this stuff is spectrally compatible. That's number one. Telco people say, oh, you want dry copper, but even if you attenuate what you're putting out, is what you're doing going to cause interference to neighboring cable pairs? Answer is no. This is much higher than any services on a line. This will actually coexist on DS1 circuitry. It won't cause problems. So if you hear that, show them some data and kind of give them an indication of the spectrum that's in use, because you will not have problems unless you have very, very weird and specific situations happen in your wiring. Unlikely to occur, but you may have some reactance somewhere, some funky reactive load or an active device somewhere that produces harmonics at lower frequencies. But that's a moot point. In most cases, if you get dry copper, neighboring cable pairs won't be influenced by your signaling. As far as the frame format goes, it's pretty self-explanatory. You have a standard 802.3 frame, destination source ether type, the Ethernet data up to 1500 bytes, and the frame check sequence, the last 2 bytes, a 16-bit CRC, is usually put in for an Ethernet frame check sequence. As far as what HPNA does differently, it takes and removes the preamble off the Ethernet frame, generates its own preamble, generates another thing called the frame control, which is a field that Ethernet doesn't typically ever have. But in HPNA, they made some significant changes to how the contention model works. Because you have an entirely shared physical medium, much like 10^2, think of it like that. Imagine a large 10^2 network in a home. With standard Ethernet, you have a situation that can occur when one station goes to transmit. It may listen for a while, see no activity, think it can grab the media. Great. Another station can wait and listen long enough and never hear that first station transmit. If they both transmit, you'll have a late collision, or maybe even an early collision if they just decide to go a little bit more aggressively. But in any cases, what has to happen in Ethernet is they both back off a random amount of time, listen to the link again, and go. Very straightforward collision avoidance. In HPNA, you don't have guaranteed situations where all nodes can hear each other equally. Between the top floor and the bottom floor, you may be only able to push about 2 megabits worth of communication. Between the top floor machines, maybe get about 8 megabits. So in a situation where characteristics between nodes are not the same like they would be in 10^2 or normal Ethernet, what do? In HPNA, the solution was to create a frame control sequence. Basically, it contains some parameters that are useful to other nodes as they hear frames come by. Number one is, as a frame is heard on the wire, all the nodes read the preamble, synchronize their internal clocks to the clock in the preamble. Basically, as the station that transmits puts a frame out, it embeds a clock signal so that other stations can recover that once they have the frame come into the cards. That's a problem synchronous circuits overcome by having embedded clocking in the actual telephone link, or the telco link. In Ethernet stuff, you can have a packet start and stop at any time on the line. There is no overall synchronization between nodes. So you have to somehow embed that in the frame. So the preamble, as it's being heard by the cards, synchronizes the internal clocks, gets them synchronized second by second or tick by tick, what have you, to the transmitter. After that happens, the frame control is the next issue that the transmitter will emit. That's a 16-symbol area, which more or less is 1 bit per symbol. It's the lowest possible data density that HPNA can accommodate. And that controls something called the silence interval. As this frame propagates through the medium, what that tells the other stations is, even if you can't hear my payload, because maybe the communication between those the stations in the upstairs computers, which can effectively exchange data at 8 megabits, the downstairs ones only understand 2 megabits. So to have it be effectively heard by all the stations, the preamble and the frame control have to all be sent at the lowest possible data density. So they're all sent at the 2 mega symbol rate, so that all the stations can hear them as a baseline. But once they hear the frame control, other stations that would normally try to require the link won't, because the frame control packet or the silence interval within the frame control area tells the stations that my message is going to this other host, and I know that when I send a message to the host on my top floor, it can respond right away. However, the station on the first floor, hearing this message whisk past, should know that the silence interval will be long enough to encompass my sent packet and a received packet potentially from my destination node. It's a very good activity. In Ethernet, every packet is a single shot. Try to get the packet out. Don't care what's happening after this. Dale?
So does it include the packet length in the framing control?
No, that's a hybrid thing called the silence interval will take into account a few things. The station's need to push data. There's 7 priority levels as well. So as far as the station's desire to push data, that will affect the silence interval. Basically, there's 4 values, 0, 1, 2, and 3. So I do this for the entire frame control area. But that basically says that I have waited this long. All the other stations should wait this much longer before they can transmit. Expect transmissions to come back from me. But that's all being controlled in the transmitter based on the application protocol sometimes, based on the driver's pre-configured settings. If the administrator said this machine should have a priority of 5, other than a priority of 6 may use a shorter silence interval or a longer one, depending on how they all want to try to avoid contention for return replies quickly. But Ethernet doesn't address this. Every packet is just put on the wire or attempted to be delivered to the wire with no regard for other packets that may come after it. In the case of TCP, you always want to push out as much as you can waiting for acknowledgments if you're a server machine. If you expect to be putting a lot of back-to-back packets on the link, your silence interval will be very, very, very short. But you're still giving other stations a chance to know when to jump in. That's the goal here. The goal is to say, as this packet floods the network, if you're going to jump in, you jump in this much later. So they don't have to go and re-listen for activity in the link. They can just acquire it knowing that all the other stations heard that message, and they're not going to try to go for the wire if their internal priority is set lower than the silence interval. So it's a very intelligent frame format for HPNA to use. So things like, for example, when we did this test at Herzing with the power bars, we were transferring SMB between 2 Windows hosts, just dropping files back and forth. Typically, if you had a slow link, 10 megabit Ethernet, railed full, you'd see a large amount of delay between those 2 machines. For example, if you pinged one host to another, you typically see 20 to 50 milliseconds of traversal delay between them because the contention to get on the link was so high. In terms of HPNA's contention model, you can always get a frame out in 2 times length of the frame. That's just a standard notion in HPNA. So if I want to deliver a frame into a pretty saturated network, the delay that I will experience getting my frame to the line is never longer than twice the size of my frame. Because I can listen for silence intervals and know when to stick it in right away. Listen for a silence interval large enough for my packet, and one of those should always occur within a certain amount of time. That's an algorithm that the users can't change. All you can change on a machine is the priority it should be given, or per protocol or per service on top of that layer. But Ethernet doesn't address this. So things like the capture effect on a large unswitched network that occur, 2 hosts can monopolize the network pretty effectively and cause insane delays or lots of retransmissions from the stations. In HPNA, that can't happen by definition. I'll see you.
10 millisecond delay shown for all the pinging between 2 hosts when we're doing the delay.
Yeah, so basically when you had 2 hosts that were heavily abusing the network, delay did not rise as high as it would for new data coming in. Think of it like this. The fuller the pipe gets, it can always back off everything else a little bit more, unbeknownst to the protocols on top of that. So TCP won't see lost ACKs, it'll just get delayed ACKs. It may slow down a little bit, but it necessarily would not need to because of lost frames or lost windows because of retransmissions or gaps in the windows, that sort of thing. So as far as a protocol to use on a multi-user network, HPNA is actually more suited for common media between all the stations than Ethernet would be, just because of the contention resolution being much, much faster. But in general, though, if you have 2 stations that are monopolizing the link, they won't monopolize it quite like it would be typically seen under Ethernet. HPNA is a lot more fair about machines getting the link and acquiring it to send their data. So anyway, after understanding all the frame stuff, which is not necessarily important for here, I had a friend of mine, Sneak, set up a loop of wire. I wanted to see how this stuff worked on a real pair in the ground to a CO and back to a location so I could have my gear in the same building. So he did this. He took and arranged 2 pairs of copper from his house to the slick hut, an intermediate distribution pedestal. Crossbox? Okay, crossbox. I'm sorry, not the slick hut. So somewhere upstream, that netted us about 3,500 feet there and back, created basically a big pair, a big loop from the house location, house and back. On the end of that wire, I put 2 HPNA bridges. I just bought 2 of the really generic, or I didn't buy 2. He bought one, I bought one for a day and returned it that weekend. Staple, yeah, any 14-day rental, I call it. So we rented these bridges, attached them to the line, and miraculously, the link just showed up. That's another thing as well. HPNA has a very intelligent thing called a probe frame, or keep alive. Every station emits, when there's little traffic, 1 probe frame a second, basically announcing itself to its neighbors. They all build a historical record, so to speak, of how the data format that comes off that broadcast is best received. For example, that little probe frame contains a sample of data at different densities. The stations that hear it can say, well, I heard this and this, but as it got denser, I couldn't hear it. So I know when I transmit to that station, I should start at this bit rate. Very intelligent, especially when you have a media that doesn't guarantee the same characteristics to all the computers on it. So those probe frames just started showing up, and both ends saw it. The link came up in about a second over this 7,000-foot loop without much issue. What's that?
Fancy ARP.
What's that?
It's a fancy ARP.
Yes, fancy ARP. Basically, it's a layer 2 ARP. Think of it like all the nodes learn the other nodes' existence and signaling characteristics between the nodes before you even send data. This can be configured in about a second. It's kind of like a modem automatically training itself to the line conditions at any one given point in time. And unlike modems, this will fall back but fall up as soon as it can as well. A station doesn't actually elect it, but the overhead, the probe frames can cause the chip to start transmitting at a higher density. So it'll fall back down, but fall up as quickly as it can too. But as far as references go, we decided to take these 2 bridges, test the big long loop, and then do a reference with the bridges just arranged next to each other through, like, say, a patch cable. So what you're seeing here is a composite of different packet sizes ranging from 16 to 1,500 bytes. As you see on the far right, that light purple-red color, that is 1,500 bytes. Next to it is 1024. Next to that is 512. Next to that is 256. And as you see, as it gets lower, the accumulations become much, much more dense. The reason the x-axis is so large is because I wanted to have all of the graphs from 0 to 14 milliseconds consistent, so we can compare them visually as you see the wire length increase. And lastly, the Ethernet reference, which is just the 2 hosts over a patch cable to show the difference in delay between the hosts themselves through an acceptably fast link. But through the bridges and back, I'm sorry, this is the Ethernet reference. I'm sorry, this is what we're seeing first. The far west right is the largest packet down to the smallest. As far as an explanation of what this graph is, the simplest way to think about it is as you watch the curve, notice on the x-axis it goes from 0 to 14 milliseconds. The vertical axis is the packet count seen at that delay on the x-axis. So for example, for 1,500 bytes, it looks like 1.5 milliseconds was the predominant delay. There's about 62, 63 packets that match that delay. As you go above it, you see it drop sharply, and there's a small little spike next to it. Explanation for that is that as packets are received by the host, there's only certain intervals that they can be brought up to the application that sent the packet. So using ping, for example, to emit a packet out, get it back, if the packet came in just after that point when the application could receive the packet, it'll catch it at a higher falsely high delay. So more or less what you're seeing is a harmonic caused by scheduling on both machines. Not sometimes the network was more lagged than others. This is a 10-foot piece of patch cable between both machines. There's nothing affecting the throughput, nothing affecting the signaling of the wires, so retransmissions never occurred really. But in any case, you still see that harmonic structure. You still see that a little bit of the packets additionally came in at just the wrong interval and were perceived as being higher delay. But suffice it to say, the higher the peak is, the higher the spike is. That's the predominant delay seen on that link. And as you go above or below that, you get some deviation. So the reference link looks like this. Even the largest packet size round trip out and back was 2.5 milliseconds. So relatively fast for normal Ethernet. As you get down towards the 16-byte packet size, the lowest was like 0.2 milliseconds. So out and back, very quick. Most likely that's the time through the driver to the Ethernet card across the wire and back. So as a baseline, that's what Ethernet looks like when you probe with a variety of packet sizes. 10-foot HPNA looks a little bit different. Over a 10-foot loop of HPNA, you see a baseline minimum delay of about 2.5 milliseconds, not that 0.02 milliseconds. This is a much higher threshold. What this is due to is a packet has to be received then the destination determined, and then based on the destination, the bridge has to find basically an acceptable density of data to put that frame onto the wire with. So there's a lookup time, more or less, kind of like a switch has when a packet is received. It needs to determine in its switching table which port contains the destination address that the packet's going to. So that lookup time gives the minimum traversal through the device a small amount of additional delay. In this case, as you get larger packets, the grouping is now much farther spread. As you saw in the Ethernet one, the separation was from, say, 0.2 milliseconds to 2.5 predominantly. So it's a very narrow spread for the entirety of the packet sizes, from 16 bytes to 1500 bytes. On HPNA, I'm sorry. On HPNA, the differences were more on the order of 6.5 milliseconds. So because of this broadband medium, basically the devices can choose a frame bitrate at any one given point in time. You get a situation where now larger packets take a lot longer proportionally than they did on normal Ethernet. So it's a very interesting way to characterize this. Comparing it to the 7,000 foot loop, even more lagged results. 1,500 bytes now takes about 13 milliseconds to get there and back versus 6 milliseconds before. So, but the point is here, HPNA is a reliable way to deliver data over 7,000 feet of wire. I expect this to probably be workable to 10,000 feet if you have the wire available. Don't have it available yet. Probably have it sometime. But in any case, HPNA does do a trick. It is an effective way to get data through. You notice on the blue colored, the dark blue colored bands, it's about half as tall as the other spikes. What happened was I was testing and did 2 tests 2 hours apart, 1,000 packets per test. The second group later on in the day experienced worse characteristics over the wire, so those 1,000 packets had higher delays. So those two peaks on the blue color, the darker blue color, are a result of half the packets essentially accumulating at a little bit higher delay and the other half accumulating at lower delay. Proportionally, it's half as high as the other accumulations that were more closely matched throughout the entire testing time window. So HPNA moves data, period, point blank. So 7,000 feet of copper. This stuff's supposed to work up to 1,000 foot max. It goes a lot farther. What's this mean to you? If you have a network in your house, chances are, if you're close enough and there's no load coils, your telco can hear every damn packet you put on the thing. Keep that in mind. If you run a home network, and even if you SSH over it or run junk, whatever you think is secure, they could still probably decipher or demodulate almost any frame you put onto the loop. So don't assume that it stops at your DMARC because it's a higher frequency signal. It still propagates. It has quite a bit of oomph behind it. True, it's 1 volt or less, probably 750 millivolts, so like 0.7 volts. Pretty quiet signal. However, it still will propagate on good enough copper.
That's only true if you're less than 3,000 feet
True.
from the office.
If you're less.
We're assuming there's a load coil.
Yeah. So yeah, the magic distance is at least 3,000 feet then, right?
Always first 3,000 feet from the office and then 6,000 feet thereafter.
That's one thing we didn't test to see if the signal will get across a load coil. For people who haven't played with load coils, what they are is basically a big transformer to couple the line to at a given interval to more or less balance the characteristics of the transmission line end to end. Keeps reflections down, keeps noise down. Generally is a more
It's a side effect of low pass filter too.
Exactly. Basically, think of it like a large transmission line. A transmission line is series inductance, parallel capacitance. If all you have is parallel capacitance, you should probably try to match the inductive load that the devices see in proportion to the capacitive load. So by putting inductors every once in a while, larger, basically what amounts to a transformer, you can better match the line or engineer the line for low frequency usages, like the voice band from like 30 kilohertz on down. That kind of stuff is what the focus is. So I haven't tried it, but from what I've been hearing now, it probably wouldn't get past a load coil.
Yeah,
So if you're close enough, or if you're in an apartment building with neighbors near you, sniff their network.
Or end bathroom.
Exactly. One thing you don't get with normal Ethernet that you do get with HPNA is something called limited automatic retransmission request, called LARQ or LARQ. What LARQ is as a frame is being sent, if you have impulse noise like a spark or a motor running, generating say 60 impulses or noise bursts a second, without LARQ, you will tend to notice the device is dropping to a very, very low bit rate almost automatically. This is a graph supplied by the HPNA.org site. There was testing done in a lab that generated random spark events or random events on a line, random impulse noises. You imagine being on the phone hearing a click or a pop. That's a noise event that could break a frame. On Ethernet, the devices would have to retransmit the entire frame. On HPNA, the devices are smart enough to say that as I was listening to your frame, I heard the noise happen here. Send me this byte range again. The devices on the link layer can do this. IP never knows about it. TCP never knows about it. So if you have impulse noise, like motors running, hair dryers running, any fluorescent lights causing crackles more or less on the line, HPNA can muscle through it and get whatever it can when the intervals are available for the data to make it through. So limited automatic retransmission request is a worthwhile algorithm to implement. But again, being done in hardware by Broadcom. So that one chipset on 3Com NICs, on Diamond Multimedia NICs, on even Linksys makes 10 megabit HPNA gear now. And the bridges, of course, they all implement LARQ. So if you have a horrible environment, you can't even extend a T1 in the same building over, or larger synchronous ones, you can get away with it by passing Ethernet over HPNA. This is a powerful notion. Lots of lines have impulse noise you can't stop. This can work around it, obviously. The graph indicates that even above 100 events a second, 9 megabits about is still realizable over this link. You're not retransmitting the entire 1,500 bytes in the frame. You're not wasting time sensitive loss. TCP won't back off that dramatically in that case. Very cool thing to have happen on the actual network layer itself. And that's it. Thank you. Questions, please.
Did you figure out how to do ATM over HPNA, or is it possible, or not because of the encapsulation?
If you put it inside of, you can re-encapsulate in an Ether type reserved for ATM over Ethernet. It does exist. Supposedly NetGraph does it on FreeBSD. Although you add on a minimum of 18 additional bytes. So you have, 48 of usable data, 5 of header already on ATM. Adding on an additional 18 isn't that bad. So you can do it if you give it a false MAC address. LAN emulation, I think it's netgraph_lane, is an available module to encapsulate ATM in a point-to-point Ethernet tunnel, more or less. And then HPNA could transport it. Natively, there's nothing stopping you actually from building your own implementation of HPNA line code, of the CLAM line code and the modulators to pass ATM cells, not Ethernet. There's nothing stopping you. You could still use the limited automatic retransmission request and the dynamic bitrate stuff. No problem. I mean, you could readapt it to those understandings of addresses instead of Ethernet addresses. You could do ATM though. That would be possible. Dale.
How many hosts can you put on a line?
That's a limit, actually, imposed by the size of working memory for each HPNA device. Obviously, they built a table of the nodes they know about. Realistically, I've seen people doing 64 or 70 nodes in a network. The HPNA org fact says 25 is the max. They're more or less saying that because of the collision of keep-alive frames. That tends to happen more regularly as you have 25 stations all broadcasting a frame at once. So it kind of beats itself up a little bit. But the bridge devices that have enough memory can, as large as the translation entries are to fit in memory, that's the only limit that we're running into. Yes?
So is your next project setting up some game servers done over HPNA?
Oh, yeah.
Sure. Yes?
Is this what Cisco's using for its last mile technology, I think they call it?
LRE, the long-range Ethernet.
Yeah, I think that's
They're using similar signaling. All that HPNA amounts to is a non-baseband Ethernet. The line code is not binary. It doesn't have just 2 states. This has up to 256 different states. So it's more analog than digital. It's a broadband-oriented signal. Occupies a much wider swath of spectrum. A narrower swath of spectrum, but still doesn't have a key component of frequency. It can be anywhere within 4.5 to 9.2 megahertz. But Cisco basically has their own version of similar signaling for encapsulating Ethernet in. It's not compatible with HPNA. That's a big downside.
Well, I kind of found that out watching their little tech thing. That is their little proprietary format, but
Yeah, their
it sounded
modems.
from what they were demonstrating. That's
Yeah.
similar, like cousin
They
technology.
missed a few things though. They didn't implement keep-alives. You have to have the devices somehow send probe frames on their own, like kind of like an ARP thing, like you.
Cisco Discovery Protocol.
Sure, CDP would seed it, but who wants to run that? So yeah, they dropped the keep-alive notion. They made it more point-to-point. They don't want to do point-to-multipoint nodes like for like an apartment complex. That's not ideal for them. They'd rather have one Ethernet bridge in the house or in the apartment and break that out over a hub. They're not about the kind of distributed fair access that this stuff gives. They also don't prioritize anything. It's missing a lot of what HPNA gives you. You can actually run voice over IP and guarantee latency between nodes of HPNA. That is built into the protocol. You can guarantee 5 milliseconds or within a millisecond of traversal over the network. That's doable. But to my knowledge, LRE doesn't address that. The only thing they do that's handy for multi-tenant buildings is they have a big switch, 24 ports of HPNA breakout. You punch that down to the phone board that's already there for the apartments, and magically they're all on the network. They do a cool thing where they isolate, like by port pair to a VLAN. So you can basically run what's called Cisco interswitch link or ISL, and say ports 2, 3, 4, 5, and 6, 7, 8, 9 on to 12 all are ISL trunk 1, 2, 3, 4, 5, 6, and so on, and have one router on one Ethernet port off that big chassis be your uplink to a T1 or something. No customers can then talk to each other, but they all see the same default gateway. They all have the same subnet for either machines. One DHCP server will handle that entire group with nothing funky. It doesn't break any rules. But the HPNA switch itself, in this case, not HPNA, but long-range Ethernet switch itself, does the separation or the partitioning of their individual uplinks. So it's basically focusing on integrated VAR stuff in multi-tenant or multiple dwelling units, hotels, that kind of stuff. I don't see it being as effective or ever as cheap as HPNA. With HPNA, you can grab barbed wire for crying out loud and get 4 megabits per second. Man, anything that's conductive, Romex, barbed wire, Mylar sheets that have like, the shiny stuff you put on growing rooms. Like, yeah, the power bars, the foil wrappers.
So we can
Yep. Ted,
outrun game servers.
what's that? What's that, Ted?
If there's any conceivable way to increase the voltage coming out of the HPNA port on those bridges.
There is a there's a line build-out section that has a regular pair of op amps that amplify the signal coming out. Conceivably, if you could change the supply resistor, operate at a higher voltage, you might get more output. In a lot of cases, you might be working in non-linear regions. You might be overloading the transmitting amplifier, so maybe create more problems than it would help. But in any case, you could maybe build an outboard amplifier that could amplify outgoing signals and maybe pre-amplify or clean up incoming ones.
Okay.
All right, I'm done.